Hi, in today's video we're looking at combined mechanics where we're using translational and rotational motion together. The typical example here is given by an object that rolls down a slope. So if the circumference stays in contact with the slope all the way down and there's no slippage, then all of the gravitational potential energy that it loses going from the top to the bottom of the slope must be converted into both translational kinetic energy and rotational kinetic energy. Now, there are two ways to go about talking about this. Energy is probably the easiest way to do it. So, if the geometry of this object is fixed, then the amount of energy that's transformed into rotational kinetic energy is also fixed. So the geometry of it sets how much energy must be required in order for it to spin. And the only way for it to get from the top to the bottom of the slope is for it to spin. So if we take the idea of a solid sphere, well, the inertia of that is given by 2/5 the mass of the sphere multiplied by the radius of the sphere. So as this rolls here, we see that it has a smaller inertia value, therefore it moves quite quickly. Now, if we replace that with the opposite end, this is a hollow ring where all of the mass is located at the full radius. There's no mass located close to the axis of rotation, in which case we end up with 1 times mass times radius squared. Therefore this object is a lot more reluctant to turn. So due to this, it takes significantly longer to reach the bottom of the slope. Now, in terms of geometries you need to know, well, for NCA they usually give you in the formula sheet the MR squared, this one, where all of the mass is located at the perimeter or circumference of this cylinder, and then it might ask you to compare it to something which is solid across here, in which case the inertia value is exactly 1/2 of the one that's above it. These two, they're very rare these days, 2/5 and 2/3 for a solid or hollow sphere. Now, if we just look at it mathematically, we can say that the amount of gravitational potential energy is turned into translational kinetic energy as well as rotation. Now we can substitute into this formula. We just, for a ring, let inertia equal mr squared, so we plug that in up and replace our I value. Now when we then lay it out, we find that mgh equals 1/2 mv squared times 1/2 mr squared omega squared. So we've got m on both sides of the equation, so we can cancel that out. Now we let the substitution here, because we're trying to look at linear velocity, so there's a ratio here for the linear velocity divided by the radius is equal to the angular velocity. Now this means that we've got r on, again, both sides of the equation. This and this are inverses of each other, therefore they will cancel. Now when we drop that out, we get gh is equal to v squared, which means that the velocity for this ring by the time it hits the bottom of the slope is the square root of g times h. You don't need to memorize this, it's just proving to you that it works. So it doesn't matter how heavy the object is or what radius it has, it just matters what shape it is, if it's a ball or a ring or something like that. Now if we repeat the same process for a solid sphere, we go through exactly the same algebra, but this time we end up with velocity equals square root of gh divided by 0.6 instead of divided by 1. So therefore we get, it's around 29 point something% increase in speed for the solid sphere. Now if the question asks you to describe it in terms of forces and motion, it's actually a little bit trickier than energy. If I were you, I'd try to use energy wherever I could. So what we have here, I've just made a little bit larger. Here we've got a wheel situated on a slope angle theta. Now we've got gravity, which acts downwards on the object through the center. And then we've got the reaction force, which is at right angles to the surface. Now when you add this vector and this vector together, you end up with a resultant, which is the red vector. So this is the thrust that is, of course, parallel to the surface that it's rolling on, and that causes it to move to the bottom of the ramp. Now if we take those three vectors and we add them together, this one and then the other one, we see we end up with the same idea. So that this vector plus this have to equal a gravitational vector. It's split in two directions. So the normal force is always, or reaction force, is always at 90 degrees to the surface. Gravity acts directly downwards, and then the resultant is down the slope. Now, what we have here is if we have a heavier wheel, it does cause a larger force to act on the wheel, but the wheel is also heavier. So as we've seen before, acceleration is force divided by mass. So if we double the force due to it being double the weight, and double the mass, there's twice as much material, it's harder to turn. Therefore, the linear acceleration stays the same. Now, if the linear acceleration stays the same, and the radius of the object is fixed, then this means that there can be no change by varying the mass of the wheel. So here we've got two different wheels, and we've doubled the radius this time. Now when we do this, then the larger wheel creates double the torque of the wheel that's inside it, right, the smaller wheel. So this means that we end up with twice as much turning force on the outer wheel. So you might think to start off with, well, that big wheel's going to go faster. However, inertia is proportional to the square of the radius. So when you double the wheel radius, you also quadruple its rotational inertia. Now, the larger wheel has an angular acceleration, rearrange torque equals I alpha, and we end up with torque upon I is equal to a half of that of the smaller one. So now we go, aha, yes, it's true. The larger wheel has half the acceleration of the bigger one. Therefore, they're not the same. But there's a final step. Now, in order to move from the top to the bottom, we don't need to consider angular acceleration. We need linear acceleration because it's traveling through a fixed translational distance. So if it has half the angular acceleration, but it has twice the radius, every time it completes a full circle, it travels exactly twice as far as the smaller wheel does. So therefore, they take exactly the same amount of time to move from the top of the slope right down to the bottom. Okay, so in conclusion, just as we have known for a long time, good old Galileo, all objects fall at the same rate. It doesn't matter how heavy they are. We've got a new one. All objects roll down the same slope at the same rate with a proviso. And that provision is the geometry has to be the same for them to take the same amount of time. Or the way that the mass is distributed around the object is the only thing that affects how fast it rolls. Okay, so reasoning behind this, it has a larger share of the gravitational potential energy in order to rotate, which is why it will travel slower if most of the mass is located around the periphery. Thank you for watching.